Welcome everybody, and thank you very much for attending this talk. What I'm trying to do, or what I want to do, give you an insight in with this talk is recent developments in the field of 3D surface analysis with deep learning, because it's kind of different to 2D learning. And I'm going to show you an approach or the approach we used for surface repair to repair 3D surfaces. Yeah. So who am I? I am a PhD student at the Institute for Optical Systems at the University in Constance. This is our campus here. We are located very closely to the Swiss border, so I can walk to Switzerland. And it's very beautiful there, so if you have any time traveling there, it's a great site. Yeah, what is my main focus? My main focus is machine learning for surface reconstruction, defect detection and repair, especially in painting, and kind of my personal interest is in medical imaging too. Yeah, so much about me. So I'm first going to dive into a little bit of how the community of that researchers in 3D surfaces and 3D surface repair is tackling problems with deep learning. So this is how you approach a problem in 2 dimensions. You have some kind of grid in 2-dimensional Euclidean space, and you can do a convolution here on this grid. So it's very easy to tackle problems here because you have this resolution. But what in the case where you don't have a resolution? So, for example, a point cloud or a mesh, or just any manifold, NURB surface, implicit surface, whatsoever. So there's no real grid where this data lives on. And how would you feed something like this to your neural net, to your deep learner? How can you tackle data like this with deep learning? And one representation that is kind of an extension of the 2-dimensional case is just simply using voxels. So what this is you add another dimension, so 2 dimensions become 3 dimensions here, and this is a binary distribution. So what this is simply if there is data inside a 3-dimensional voxel, it is a 1, and if there's no data or no surface inside this voxel, it is a 0. And you can use these voxels to feed them to neural nets. Convolution is easily defined because it's quite like the same as a 2D convolution would be. And even if you look what the neural nets are learning here, so this is a neural net that is trained for, deep neural net that is trained for object classification. And if you look at the top layers, these are kind of like edge detectors, blob detectors, so things that you know from 2-dimensional problems, from 2D convolutional neural nets. And the deeper you go, the more abstract you get, and this is true for 3-dimensional, for voxel-based neural nets too. So up here in the deeper layers, you see chairs, screens, whatsoever. So this works kind of like a 2D neural net. Another representation which is kind of like a cheat. So what you do here is you take snapshots out of different directions and snapshot your 3-dimensional object and simply use these images, so the 2D representation of your object, to feed into a neural net, in this case for some kind of classification task. So this is a cheat because yeah, you are working on 2-dimensional data, not really 3-dimensional data. You can do this for hand gesture recognition too. Here, these are depth maps, and yeah, still you only feed 2-dimensional data to your neural net, which is based on 3-dimensional data in the background. And one very interesting approach, which is graph signal processing, and on surfaces you have something, you can define something called a graph Laplacian, so a Laplace-Beltrami operator. And what this is the divergence of the surface gradient. So visually you can think of it, if you pour water on your surface and the water flows along your surface and it will accumulate in sinks and stuff like that, this would be your graph Laplacian or your Laplace-Beltrami operator, so the surface flow. And the cool thing about this surface flow is that the eigenfunctions of this graph Laplacian, they generalize to a Fourier basis. So this is a spectrum of your surface. So you do signal processing and can do signal processing on your surface, which is really cool. And convolution is defined in the spectral domain. This has been known for many years, but the problem here is that filters, so if you train convolutional filters on these eigenfunctions of your Laplacian, then they are base dependent. So you can train them on one surface, but if you try to apply them to another surface, that won't work because they are base dependent. And so there is a multitude of work, and here is one by Masky et al., that we're trying to localize and make this base independent. So what this is they are using geodesic polar coordinates. So this is the concept that you know from two-dimensional convolution, from convolutional nets there. So correlate with a template. So you have these geodesic polar coordinates, and you move them along your surface, and you train them. They have some weights. They have rotations, so this is the orientation. And for pooling, you can just simply take away rotations of these geodesic polar disks. So yeah, now we have a localized and base-independent convolution across our surfaces in the spectral domain, and this is very cool. I have another slide here with datasets. Datasets for 3D training of deep learning are very sparse right now. So there are mainly two main datasets, which is the Princeton ModelNet and ShapeNet. Princeton ModelNet is a larger dataset, and the ShapeNet is a smaller dataset, which only contains discrete data like meshes and so. But what was the problem we were facing? We had these surfaces, very highly detailed surfaces, which had a base geometry. So you see some kind of curvature, maybe a gap here and there. And you have this detail geometry, which is the texture here, this leather texture. And this is not only a texture, this is a three-dimensional texture, so you can feel it. So you have a detail geometry and a base geometry. And these surfaces, they are used for production processes. And they get defects. They get scratched, bumps, defects of any kind. So our goal now was how can we detect those defects in 3D and then autonomously repair them using deep learning. And here's the surface, just to give you a glimpse on how they look. Here you see defect, and those are very high resolution surfaces, so millions and millions of vertices, no resolution there. This is a mesh, so it's very difficult to even process those surfaces with so many vertices. And so we decided to break down the problem in two smaller problems. So in the first step, we did surface separation, so as to separate the base geometry, so the approximate geometry of the surface, and the detailed geometry. And here in the detailed geometry, what you see is that there's a defect I've shown you in 3D, but now we have still a 3D model, our base geometry, but our detail now is a height map, so a grayscale representation of our 3D detail surface. And after separation, so this is really kind of like the cheat I was talking about earlier. After the separation, we can process our detailed geometry height map with deep learning. And that is very cool. So I'm not going to go into detail on separation. We use deep learning here for separation, but due to time constraints, I will only talk about novelty detection and multi-resolution neural nets for in-painting. So first you want to detect the defect. But the problem of novelty detection is that you don't really know what is defective and what is healthy. So we don't really know what healthy detail should look like, what healthy surface should look like, and we don't know how the defects look like. But what do we know? In our special case, we knew that the textures we were looking at should be ergodic. And ergodic means if you have some kind of window and slide this window over your texture, then statistics inside this window should stay the same from window to window. So a steady statistic over the complete texture. And the cool thing here is now, because we have 2D, a grayscale image, what we did then was we built an ergodic set of textures, of training textures, two-dimensional grayscale textures. So these are not height maps, these are two-dimensional images of textures just in grayscale. And then we train something called an autoencoder. Many of you might know an autoencoder. What an autoencoder mainly does is it reconstructs what you give him. So you give the autoencoder some kind of image or some kind of data, and the goal of the autoencoder now is to reconstruct what you gave him in the end. So that's not a hard task. Just take the input, show it at the output, problem solved. But if you apply some restrictions to the autoencoder, for example, you go smaller and smaller in the intermediate layers of your neural net, this autoencoder has to find a very good compression of what you are giving him. So, and we used this to detect our defects. So the main idea here was if we train the autoencoder simply on or strictly ergodic textures, it should only be able to reconstruct ergodic textures. So if we show it some kind of defect or defective texture or texture that is not non-ergodic, it should fail and the error should go through the roof. And yeah, that works. If we slide the window over our height map in this case, we can then separate two classes. This is the error here shown in a graph. And the orange dots are our defect. So if the window slides onto the defect, our autoencoder is not able to reconstruct properly and our loss goes through the roof. And that's the orange dots here, and the green dots here are our healthy windows, our healthy texture. So we now know where the defect is located on our height map, and we want to now reconstruct or in-paint our defective region. And what we use for this is something that was developed in Tübingen by a group around Leon Geddes. And they use two neural nets, so one activation network and one synthesis network. And what you do here is you show some kind of texture. So we have the healthy texture now separated from the defect, so we know what healthy texture should look like. And you show the healthy texture to the activation network. Out of the activated convolutional filters, you compute a statistic measure, which is called Gramian matrix or Gramian matrices. And then on the synthesis side here, you activate with some kind of image or Gaussian noise or something. And you say, please optimize your convolutional activations or your filter activations now. Please optimize the input image so that the activations of those convolutional filters correspond to the activations of our activation network. So the Gramians or the gray matrices the distance between the gray matrices shouldn't be too large. And you all know an application for this. This is an application for this synthesis. So here what was done is simply activating the synthesis network with these houses over there, and in the activation network here the activation network was activated with a Van Gogh image, and then in optimization the input image was optimized so that the statistics were as close as possible to the statistics of the activation network. And we use this for defect detection, no, not for defect detection, for in-painting. So our problem here is we have a very high resolutional height maps. So 4 megapixels, 6 megapixels, 9 megapixels whatsoever, and you can't really feed resolutions that large into a neural net because you couldn't train it. It's as simple as that. And because of that, we needed to develop some kind of windowing for that too. And we also needed to, if we have some windowing to in-paint the defect, we need to make sure that we satisfy the global statistics, which are these dots, and we need to satisfy the local statistics, which can be seen here, which is this fabric. So I show you an example of a color image right now. This is not really a height map, but a color image, but it works on color images too. So that's why I use this example here. Yeah, what you can do now is you can slide a window over your defect region, and we then optimize the defect region so that not only the local style or the statistics for the local style are satisfied, but also the statistics for the global style. So we have multiple networks with multiple resolutions looking at our synthesis or at our healthy texture and then optimizing the defect region so that so that the synthesis here really reconstructs what should be there, so to repair the defect in the end. This is the result here. So this procedure has 2 steps. So first we satisfy the global statistics, and this is the just simply the dots here. And in the second step we apply the detail to satisfy the local statistics. Yeah, and if you look at the result, this is an in-painting result, a windowed in-painting on a color image, and the result looks really promising. But now back to height maps. Can we use this for height maps? And as it turns out, yes, it works very well with height maps too. So here, this is our height map separated from the base geometry, which I've shown you before. And here on the right, you see the in-painted version, the reconstructed version with our multi-resolution neural network. So a very cool result here. And in the end, I'm going to show you just how this looks back on the surface. So if you now take the height map back onto the base geometry and apply it back on the base geometry, what you get is this. And this is, these are not connected yet, so the in-painting region is not connected to the healthy structure yet. But as you can see, this is a beautiful, so the network has done a beautiful job on in-painting here and repairing the surface in the end. So yeah, so much on our work, but what do I think well all of this is leading? So I've shown you you can use voxels to train your networks. You can use 2D representations of your 3D surfaces, so kind of like we did it, or simply take snapshots of different directions. But ultimately what I do think is that in the end we will define neural nets directly on surfaces. And the approach in the spectral domain is something that you should keep an eye on if you're working with surfaces in deep learning. So I think this is the direction we're going. And I want to direct you to 2 very great papers. One is by Michael Bronstein, which is called Geometric Deep Learning Going Beyond Euclidean Data, which covers most of the spectral domain deep learning. And a very cool paper of last year's NIPS, Convolutional Neural Networks and Graphs with Fast Localized Spectral Filtering, which is convolutional neural nets directly applied onto graphs. And if you think about a mesh, ultimately it's a graph. Yeah, so thank you very much.